Hi everyone, I'm going to record a bunch of examples for exam 4, and these are sample test questions basically. Let me know if you have any questions by posting to the discussion page. So the first one really is a chapter 2 question. What is the formula for iron 3 oxide? And we're going to do it like a chapter 2 problem on the test, but I'll explain it more from the periodic table and electron configurations perspective, just for completeness, right? But when you do it, you're just going to do it like we did before by memorization. So iron 3 oxide, what's the formula? Well, this 3, that now that we've done oxidation numbers, that's the oxidation number. That means that is a +3 ion. +3 iron. How's that? So Fe3+, right? And then what we needed to know in order to put this together is what the oxygen is. So in chapter 2, we just said oxygen is in group 6A, and we're going to know that that's a -2 ion, right? And we'll just stick it together like that. So iron, if it's +3, this is a -2. It has to add up to 0, so that's going to be this one, right? But then in this chapter, we want to know, why is it that oxide's always a -2 ion when it's in an ionic compound? Well, the electron configuration for an oxygen atom, if you go through and do the electron configuration, it's 1s2, 2s2. Wait, we got to figure out how many electrons are in oxygen. Forgot to even do that part for you, right? So we'll pop up the periodic table. Oxygen has 8. All right, 8 electrons. And so 1s2, 2s2, 2p4. Got ahead of myself, didn't I? And, you could do it by the 8 electrons in the filling order, or, right, you can look at the periodic table and just say, oh, I'm over here in the p subshell, 1, 2, 3, 4 electrons in the p subshell. That gives me that, right? So then why is it that when it forms an ion, it is -2? Well, it's going to gain 2 electrons until it has a filled S and P subshell and the noble gas configuration. All right, so that's the idea, right? So we'll add 2 electrons to fill the P subshell and get that noble gas configuration. So that's why oxygen's -2, and there's our formula. But again, you don't want to go through all this stuff on the test. We're going to know that the group 6A is a -2 ion. Okay, and that's that one. All right, so next test question. So this one's guaranteed to be on the test, right? And there were a number of these in homework where you had to do it for a whole molecule. We'll do it both ways. So how many valence electrons does iodine have? You just look at the periodic table for whatever atom you're given. It's in group 7A, so that means it has 7 valence electrons. And again, I hope that you're doing these before I should have reminded you, pause the video and do them, because it's good practice for the test. I've got this posted as a handout. You should work them, come back and do that. I forgot to say that this time, darn it. All right, so now the next one, we haven't done a ton of, here we go, of these periodic trends ones. Now, the homework for periodic trends, I didn't even get any questions about it. And I hope that's not because you can just click on the multiple choice and figure it out that way. Make sure you understand and can do this on the test, right? But the homework went really well, so I'm assuming the class knows how to do this. But make sure that if you were one that was in a hurry and just wanted to get the homework points and just clicked until you got the points for it, make sure that you go back and understand how you could get those. All right, so rank these atoms in order of decreasing size. Potassium, chlorine. So I've got my periodic table here. And the increasing size, let's see, we know it got bigger that way, right? So because you're filling up larger and larger, the principal quantum number tells you the size or the energy of it, and you're adding in more electrons, right? So it's getting into higher, bigger orbitals. So it gets larger that way. Do you remember that it also gets larger this way? Okay, and so you want to memorize that separately from your understanding of it, and that will help you to remember the explanation for it. And the explanation was that as you go across a period, the shell pulls in tighter because you're adding protons to the nucleus. It's more and more positively charged. So those electrons that start out in about the same size shell are pulled in, more attracted to that positive nucleus. So it gets smaller as you go across, which means it gets larger this way. So that's the trend, and we'll just memorize the trend separately from our understanding so that we don't make any goofs, right? And then we just need to put, look at the periodic table, and I think chlorine's above bromine, right? I should just pull it, since I can show it, I could just show the periodic table on here. And then potassium's over here in group 1. And so that's what it looks like. That's the trend. And so in order to do this, let's see, it gets bigger this way, this way. So that means that between chlorine and bromine, bromine's bigger, right? See if I can get this right. Bromine is bigger than chlorine. What about, let's make sure potassium's in the same row as bromine. I'm pretty sure it is, but let's just double check. Yeah, good deal. There's potassium, there's bromine. Okay. So that means that potassium is bigger than bromine, right? Because it gets larger as you go this way and down. And so that looks pretty good. Of course, it says list them in order of decreasing size. So do we have that answer? Yeah, good to go. So you just make sure you check, with the greater than versus less than. If it, it could have said increasing size and then everything's flipped. All right, just double checking on that. Let's see, what was the next one on that handout? I lost my sheets here. Oh, here it is. No, I do not have the sheet. Uh-oh, how embarrassing is that? Oh, here it is. I accidentally threw it on the floor with the other ones. Draw the Lewis structure for nitrate. What is the formal charge on nitrogen? So here's one we're going to get a little more slowed down, right? Because we got to draw the Lewis structure. Let's do that then. So nitrate, NO3 minus. Let's count the electrons. So nitrogen has 5 valence electrons because it's in group 5. There's 3 oxygens, and oxygen's in group 6. And then we have a -1 charge. So -1 charge is 1 electron. All right, so that means we've got 24 electrons. Did I do that right? I sure hope I did. 24 electrons. 3 times 8, 16. Okay, yeah, good. And that's 12 pairs. Okay, so now drawing this, nitrogen's going to be in the middle, and oxygen we're going to connect with single bonds, right? Now let's just add in the rest of the pairs around the outside of this ion, okay? And we're trying to fill the octet rule, but I'm just going to add them in willy-nilly and then move them around. So 12 pairs, we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in doing that, I've filled the octets on the oxygen. But we know that nitrogen also has to have a filled octet because it's in that second row there. It's carbon, nitrogen, oxygen, fluorine have to follow the octet rule. It can't be electron deficient. And so this is not the Lewis structure for nitrate. We've got to fill that octet for nitrogen. And so we're going to do that by taking a lone pair off of oxygen and moving it into a double bond. And we could pick any one of these three. I'm just going to take this one and move it in like that. Slide this up and redraw it. Okay, so that is our Lewis structure, and it follows the octet rule, right? If you look at this, oxygen 1, 2, 3, 4 pairs, 8 electrons, nitrogen 1, 2, 3, 4, and so on. It's all good to go. So let's make sure that that's not like looking like it's together. All right, so now on paper, remember, we'd put the square brackets and we just put the minus charge over the whole thing. And I like that, but that's not how you draw it on the computer drawing program, remember. So make sure when you do these that you do it. There's a video about how to do the ozone ones, for instance, in the instructions. Got a lot of questions about how to get that to work. Anyway, so assigning formal charges on computer drawing software, we have to assign the formal charges rather than putting it on the whole thing. And then formal charge is another, just a separate question like this one. You know, this is a good test question. What's the formal charge on that? Okay, so, and on the test, just so you know, a lot of times I will give a Lewis structure and ask to assign the formal charge, like those ones in the homework. But this is also a good way. It's hard to have you draw Lewis structures on a test, right? So I have to give you possible Lewis structures, or say if you draw the Lewis structure, what would you get? All right, so now assigning the formal charge on the nitrogen. The way we're going to do this is nitrogen's in group 5A. And so that means the neutral atom has 5 valence electrons. That's the neutral nitrogen. Then we're going to count how many nitrogen has in the structure. So now a lone pair counts fully on an atom for formal charge purposes. It's owned by that atom. But the bonding pairs are shared. And so for counting charges, we're going to have to split those back up. So the way we do that, the way I counted it, is just when you see a bonding pair, you just count 1. You split those 2 electrons up. So I look at nitrogen, I just go 1, 2, 3, 4. Nitrogen has 4. So then it has 4. So it's supposed to have 5. It only has 4. So what's the, and I know there's formula on there, needs and whatever, that some people use. That's fine if it works for you, but I don't think you need it. Right? 5 valence electrons, it has 4. So it's missing 1, isn't it? It's missing 1 electron. So we're going to put a little plus on there. Okay? What if we had to do it for the oxygens? Same thing, right? Oxygen's in group 6. Supposed to have 6. How many does this oxygen have? It has 2, 4, 5, 6. See how that works? So that one's 0 formal charge. What about this oxygen? It's supposed to have 6. It has 2, 4, 6 for the lone pairs, and 1 for that. So 7. So that's a minus, isn't it? Okay. Maybe I'll put the 1s on there. I don't think they show up on the computer drawing software. So that's a -1 formal charge. That's a +1 formal charge. And this one's going to be the same, -1, because it's got the same 3 lone pairs and the bonding pair. All right, and then you can check it, right? Because the formal charges have to add up to the charge on the ion. So -2 + 1, so it's a -1 total, and that's our nitrate, right? All right, so those were the examples on the handout, but I think that I have another good example here written down. Let's see if I can find it. So I'm going to go back to like normal paper here. And so this one's not on the handout. I just wanted to go through one more example for you. And so we've got this molecule. I forget the name of it. Darn it, I didn't write down the name of it. I just wrote the structure. So we're going to work through this molecule. and get, let's see, let's do the hybridization. And we'll do it all the way across. And we'll get the electron geometry, and we'll just pick, one central atom or a couple ones to talk about. And then the molecular geometry. And then I was going to talk about bond angles too, that you would get from that. And that's mostly just knowing that table. Okay, so the first thing, in order to do this, we'd have to draw the Lewis structure, right? And so let's draw the Lewis structure for that puppy. And I know some of the Lewis structures like this would be challenging, and you might need the backbone. I try on the test. I mean, this is introductory general chemistry, to give you one where you just have a central atom and then the things around it. It's a little harder for us to know the backbone for something like this. The key is that the hydrogens are on the outside. They can only be connected by one bond. And so those hydrogens are on the carbon. Maybe I'll do this in blue to show kind of how this works. So that means this carbon is actually connected to that next atom. The three hydrogens are on the carbon's connected to the nitrogen's connected to the carbon's connected to the oxygen. See how that works? And again, I think that would be a challenging one. Let me see if I got a little better marker here. Yeah, this one's a little sharper. We'll see. Okay, so to draw the Lewis structure, our backbone is going to look like this. Carbon, nitrogen, carbon, oxygen. Okay? And then the hydrogens are going to be connected to this one with a single bond. Thought that one was sharper. It's actually thicker. It'll be fine. Oh, I forgot to count the electrons, didn't I? I was going to cheat and do this the organic chemistry way of drawing Lewis structures, but I didn't teach you that yet. Oh my goodness, I apologize. So we got to count valence electrons, don't we? Let's count the valence electrons. Is it okay if I just do that verbally? Right? Because you can look at the periodic table and see that carbon's in group 4, so that's 4. 3 for the hydrogen, so I'm at 7. 5 for the nitrogen, so that gets me to 12. 4 for the carbon, that gets me to 16. 6 for the oxygen, that gets me to 22 electrons, valence electrons, or 11 pairs. Does that sound right? Okay. Sorry I went through that so quickly. You just go by the group numbers, right? Carbon's in group 4, nitrogen's in group 4, oxygen's in group 6. You just add them up. You get 11 pairs. All right, so now when we look at this, 1, 2, 3, 4, 5, 6, we've used 6 pairs. We need to start sticking electrons on there, and you can see we've got, a lot of places to put them. I'm going to try and stick to my way of doing it, where I'm going to stick these on the outside as lone pairs and then move them into bonding pairs as we go. How many did I count? 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, heck. Let's just do like that. 10, 11. Okay. Not a good Lewis structure, but it's a start. All right. So I always start towards the outside, putting the lone pairs on, and then just add lone pairs. So when we look at this as we're going through, well, this first carbon, its octet is filled, right? 2, 4, 6, 8. The nitrogen doesn't have enough. It's got 2, 4, 6. The carbon doesn't have enough, 2, 4, 6. The oxygen has enough, 2, 4, 6, 8. So how are we going to fix this? Well, first thing, oxygen's got a lot of lone pairs. Why don't we take one of those and stick that in? Let's see what that gives us. So I'm going to rewrite that down here. Carbon, nitrogen, carbon, double bond, boom, boom. Let's see what we get with that. Okay. So did that get us very far? Well, I think so. This carbon's still okay because it was before. This oxygen's still okay because it just shared its lone pair. It didn't lose anything. It's just sharing it. And now this carbon is full, 2, 4, 6, 8. But the nitrogen still isn't. So does it make sense that we could take this lone pair on carbon and stick that one in there? Okay. So now let me get another, I ran out of paper here, another blank sheet of paper, and I'll rewrite that. Okay, so let's rewrite that Lewis structure. All right, so I think that's the Lewis structure that we were talking about, right? Is that, get them side by side. Just move that over. Looks good, right? All looks the same. Okay, I think that's good to go. So now, what atoms should we do? Well, let's do them all. Let's do hybridization. Hybridization. Let's label our carbon. So let's say this is carbon 1, this is carbon 2. Okay, so we'll go through like that. And just as an example, so we got carbon 1, we've got the nitrogen, we've got carbon 2, and then we've got the oxygen. Might as well do all of them, right? We can do that. So what's the hybridization? Remember, hybridization, the way we're going to do that is if we have 4 groups, and this is a summary table that's, of course, in your notes. 4 groups was going to be sp3 because it requires 4 equivalent orbitals. One of the s's, all 3, well, there's only one s, come on. One, the s and all 3 of the p's adds up to 4 equivalent orbitals. And then if we had 3 groups of electrons, then it's sp2. And then if it's 2 groups, that's sp. Right? And so this is not, I mean, there's a lot of chemistry behind it, but as far as applying it, I really hope, if you're confused at all, please let me know in post. But I really think that this is a question that the class should get 100% on. If you just know 4, 3, 2, and don't fall for any of the fishhook things with D's and things like that. Okay, so we look at this carbon, and we just go 1, 2, 3, 4 things. There's 4 things on that carbon, right? So that's sp3. The nitrogen, how many things are connected to that nitrogen? Where there's the 2 carbons and there's the lone pair. 3 things, sp2. How about this carbon, carbon number 2? How many things are on that carbon? Well, there's 2 things, 2 groups of electrons, the oxygen and the nitrogen, 1, 2. So that's sp. It's not bad, huh? This is not bad. This is doable, I hope. As your coach, I feel like these are layups. I hope they're layups for you. If they're not, please let me know. Maybe they're left-handed layups. I don't know. Oxygen, 1, 2, 3 groups, right? A lot of chemistry is hard, but I really do think that this is something that everybody can master and get right on the test. Okay, so now, and then it's just remembering all the stuff, which I realize is a lot, right, for the geometry. So what was the next question? We're going to talk about electron geometry. So let's pick one in this case. Let's do the nitrogen. Okay, so nitrogen is sp2. What is the electron geometry? What would be the electron geometry if it's sp2? There's 3 things. So 3 things as far apart as possible. That was nitrogen with boom, 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 right? 3 things in a flat plane, trigonal planar. So it's a triangle and it's all in the same plane to get as far apart as possible. So when we were doing the Vesper stuff. All right, let's see, what's the molecular geometry? What is the molecular geometry? So on one of these nitrogens, we've got a carbon, carbon 1. On another one, we've got a carbon 2. And then the other one is just a lone pair. It's just got electrons, right? So when we name the molecule, we name the shape of the atoms. So it's trigonal planar electron groups, and the lone pair is what makes it that shape, but the molecular geometry is bent. Okay? Then what about angles? What would that bond angle be? Three things in a circle, 120 degrees, right? As far apart as possible. So that adds up to 360. Okay, and you can do, and maybe you should do, go through the geometries for all the other ones as well. Well, can't really on an and atom, but you can do it for this carbon and this carbon. Hit pause and I'll just say it verbally. Okay, hit pause, come back. Carbon 1, what's the electron geometry? sp3 is always tetrahedral. And then there's no lone pairs, so the molecular geometry around this carbon is also tetrahedral. What about carbon 2? sp means it's linear. Two things as far apart as possible is a straight line, 180 degrees, and it's linear molecular geometry too. All right, well, hopefully these examples help. Good luck on the test, everyone. Please post any questions to the discussion page. That way I can help as many students as possible prepare. All right, thanks.